All right. So where we left off last week. Oh, yeah. Yeah, they're already posted. So the ones for this should be up. I just put them up this morning, though. Yeah. And the slides are up for this week as well. I'm not positive. When I post the slides at the beginning of a week, we may not cover every single slide because it kind of depends on how much we actually go through in the class, but I kind of make my best guess at the beginning of the week. Today is only one lecture, so it's fairly easy to guess. But last week we finished with paths and graphs, right? Dijkstra's algorithm, Bellman-Ford, and so on. And so now we're going on to greedy algorithms. And Dijkstra's algorithm is kind of an example of a greedy algorithm, but we're going to go through some more greedy algorithms. And in some sense, this chapter is just a chapter of examples of greedy algorithms. Basically, what a greedy algorithm is it kind of makes the best choice now without fully considering its consequences in the future. Right? It's like I optimize for today without worrying about the effects for tomorrow. That's being greedy. And sometimes being greedy can be a very bad idea. Oftentimes in life, it's not a great idea, but there are problems for which a greedy algorithm is optimal. And one of the prototypical examples is the minimum spanning tree problem. So in the minimum spanning tree, we're given an undirected graph with edge lengths. And you want to find a subset of the edges that connects all the vertices and has minimum total length. So when I sum up those edges, the sum is minimum among all subsets of edges that span kind of all the vertices. So subset of edges with minimum total length. Okay, so let me draw just a quick example of this. And we'll actually use this example again in a moment. So I'm going to draw some vertices and some edges. And it's just a useful example because it shows some of the issues that come up. So it's got 6 vertices. 1, 2, 3, 4, 5, 6. And undirected edges, right? So now there's edges like this. Sorry. Edges, edges, and then these diagonal ones. Like that. And the lengths on the edges, I'll draw them in blue. So it's 3, 1, 7, 1, 2, 5, 3, 5, 4. And then a solution to the minimum spanning tree problem is a subset of those edges, such that I can take a path between any pair of vertices using just those edges, right? And it turns out that an optimal solution to such a problem will always be a tree, as long as the edges have non-negative length. And so here's one candidate solution. I go, let's say I include that edge, it only has a weight of 1. So I'm trying to use kind of the short edges, right? I haven't yet told you what an actual algorithm is for this. But that set of edges has a total weight of 4 and 8, 12. Is that right? We have 1 plus 1 plus 2, that's 4, plus 3, that's 7, plus 5, that gives us 12. And maybe there's a better solution, but that is a solution to, I mean, that's a candidate solution, I guess, to this problem, right? And so now the question is, how do I find the shortest possible set of edges? And one thing you can notice is that the shortest set will always, in this case, it forms a tree. And this is always true. Always true, assuming the edge lengths are greater than or equal to 0. If you have negative edge lengths, then it starts to it's not such an interesting problem because you actually benefit from adding more edges into your solution. And the property this relies on looks like this, that if I have a cycle in a graph and I remove one edge on that cycle, it cannot disconnect the graph. So why is that true? So property, removing a cycle edge cannot disconnect a graph. Maybe you can immediately see why that's true. This is an undirected graph, right? So we have a cycle in the graph. Basically, if I remove one edge in the cycle, now I have that cycle becomes a chain, right? And so any path that used that cycle edge could now just use the chain, since it's an undirected graph. That's the whole argument. I'm just going to write that down formally, but so I couldn't have lost, if there was a path before, there's still a path afterward to get between any pair, right? So that's not a pen. Consider a connected graph G and a cycle. I'll just write the cycle as V1, V2, up to Vk and back to V1. Since G is connected, there's a path between any pair of vertices. And so now suppose we delete a cycle edge. Let's say Vi plus 1. Then the path that goes Vi plus 1, Vi plus 2, up to Vk, V1, up to Vi, still connects still connects Vi and Vi plus 1. I kind of wrote that backwards, like the path I wrote in the order, it takes you from Vi plus 1 to Vi, but it's an undirected graph, so I can actually just take it that way, right, to get from Vi back to Vi plus 1. And so any path that used the edge Vi to Vi plus 1 can now just use that sequence going from right to left. And so I still have, those two vertices are still connected. Any path that used Vi plus 1 can instead use, maybe I'll just call that chain star. Therefore, still connected. Okay, fairly simple argument. Like I said, I think I described it to you in 10 seconds and then took 5 minutes to write it out, but it's still useful to write it a bit more precisely. So this result implies that we can just look for trees. That's the name, the minimum spanning tree problem, right? It's that a solution will be a tree for this problem. And so the problem looks like this. Your input is a graph G along with edge lengths that should be non-negative. It's not saying that there, but I should really write that they're greater than or equal to 0. And the output is a tree. So the tree has the same vertex set and uses just a subset of those edges that minimizes the sum of the edges in the tree, right? So I'm summing up over here, E prime are the edges in the tree, and I'm summing up over that E prime, right? This is in the greedy chapter. So the first algorithm that we're going to propose is called Kruskal's algorithm. And yeah, I realized you can't see it, but when I posted these notes, I wrote Prim's algorithm. The second algorithm we're going to talk about is Prim's. So the title of this set of notes is actually wrong. It's because it says MST and Prim's algorithm. It should say MST and Kruskal's algorithm. I always get the two names mixed up. So in Kruskal's algorithm, it's greedy. So what do? If I wanted to be greedy, what should I do? Just add the shortest edge, right? And then kind of just keep adding the shortest edge. The only problem is I know I have to find a tree, so I shouldn't make a cycle. So that's all Kruskal's algorithm does. It says, start with an empty set of edges, and then just repeatedly add the shortest edge that doesn't create a cycle until I get up to a connected graph, right? I've spanned all the edges and then I stop. Spanned all the vertices and then I've stopped. Okay, certainly it's a way to do it. Let's go back to the example I gave you before and just run Kruskal's algorithm on that graph. So I'm going to steal I'm going to try and copy this. Bring it down here. Okay. I might get the same solution, but let me delete the pink stuff. Okay. Like that, right? So what I do, really, I'm considering the shortest edges one by one. So really, I'm just going to make a list to start of all the edges in sorted order. And then we'll just go through them one by one and check, add it, oh, can't add it because it creates a cycle, and so on. So the edges then are going to be, in this case, are the shortest edge first is 1, 2. There's actually two edges of length 1, right? There's 1, 2, and 4, 5. But 1, 2, that doesn't create a cycle, so I just add it. Next, I try 4, 5. It's the next shortest edge. Again, doesn't create a cycle. All is good. Now I've got just one edge of length 2, right? Which is 2, 5. So add it. Now I have the edge of length 3, 2, 6, I guess. Again, add it. Next, I also have another edge of length 3, which is 1, 4. but that would create a cycle, right? So I don't add. So I'll just put a little X above it to say no adding. Then edges of length 4, we have 5, 6. Again, that would create a cycle, right, of length 3. So don't add that. Next is, I just have the 2 edges of length 5, right, which is 2, 3, and 3, 6. To mix it up, I'll consider 2, 3 first. That creates this edge. That's all good. And then finally, 3, 6, which now would create a cycle. And one thing you notice, right, I think just based on the way I did this, is that the minimum spanning tree in general is not unique, because I could have instead of adding 2, 3, I could have added 3, 6, right? And that would have given me another tree of equal length. Okay. So there's 2 big questions to fill in. I mean, this is a nice idea for creating a spanning tree. One is it optimal? The answer is going to be yes, but we should convince ourselves of that. And then the second one is, how should I actually implement this? You know, visually, we're doing this cycle check by saying, okay, yeah, do I see a cycle in the graph? But computationally, how should I implement this like check a cycle thing? Yeah. Did I skip one? Oh, yeah, thank you. Yes, sorry. Yeah. At the end, you're right. There's one more edge to check, which is 1, 5, and it would also create a cycle. Thanks. Right, we know one way to check if a graph contains a cycle, which was run depth first search and check for a back edge. But that doesn't seem like a great idea, because here I'm going to have to do that every time I try to add an edge. I would have to run a whole depth first search, check for a back edge, you know, spend big O E plus V time. So there's going to be a much better way to do it, but the whole thing is going to be how to develop that. Yeah. I think you're on the right idea. We're going to actually introduce a data structure to kind of do the work for us. And the data structure is basically going to keep track of connected components in the graph. And then it's going to ensure that anytime we add an edge, it goes between connected components, because then it can't create a cycle. They had no edges between them before. And so this will be our data structure, and I'll go through how it works. But first, we should do something about figuring out that this algorithm is correct. And I'm actually going to prove something more general. And then it's going to also show us that the other algorithm for doing a minimum spanning tree, which is Prim's algorithm, is also correct, because it just is a different way of kind of using the same structure, which is called the cut property. And the cut property, I'll admit, is a little hard to read. So we're going to go through it, and then we're going to prove it. But the idea is this. So let's say I have a partial solution, basically. I have a set of edges, X, that are part of a minimum spanning tree of a graph. Pick a subset of vertices. So X is a partial solution, right? Now I pick a subset such that in that partial solution, no edge crosses between the set S and all the other vertices. So V minus S is all the other vertices in the graph. Then if I add the shortest edge that crosses between these two pieces, between S and the rest of the graph, and I add that to X, that must also be part of a minimum spanning tree. So I think a picture will help here, but that is what this is saying. So if E is the shortest edge crossing between S and the rest of the graph, then X union E, so add that edge E to my set X, that's also part of a minimum spanning tree. And it's using this language part of a minimum spanning tree because as we saw, the minimum spanning tree is not unique. So like, we can't really talk about the solution, right? There could be multiple. So let me draw a picture that kind of like a simple picture that shows the idea. Let's say that I have a graph. And let's just say the edge lengths are like the length of the line that I've drawn on the paper. And let's say my partial solution is, this edge, and this edge. So this right here is my X. Now, I want to define a set S such that there's no edges in my solution crossing from S to outside of S. So a candidate is this set here, right? So that's S, and then over here is everything else, right? V minus S. And now I take the shortest edge that crosses between S and V minus S. It's this one here, right? So let's call that E. And then X union E is part of a MST. Okay. So this is called the cut property because we think of this like right here as being a cut in the graph between S and that separates S and V minus S. And then we're adding the shortest edge that crosses the cut. That's the terminology that's used here. Okay. So a cut is a partition of V into two groups, S and V minus S. Yeah. So S is just a subset of vertices. Like in this case, S is, if I number these, is that what you're asking? Maybe. Yeah. Yeah, so like here, maybe these are the vertices 1, 2, 3, right? Then S is the set 1, 2, 3, and V minus S is the set 4, 5. Yeah, because X is a set of edges. So yeah. But it's a good question, right? Like this is why I think the statement of it's a little bit confusing because we've got this set of edges, we've got these sets of vertices, and then we're talking about this cut, crossing it, and so on. So let's now, sorry, just checking the time. Let's now try to prove this. And the proof isn't too bad. So we start off with what we know. The statement was that X, the edges in X are part of a minimum spanning tree. So we get to start knowing that, right? So Edges of X are part of an MST. Let's call that MST T. Now we add the shortest edge, E. So if E is also part of T, then everything's good, right? We just added another edge in T, and so like there's nothing to prove. So the interesting case is where, let's say E is not part of T. And then we're going to show that E has to be part of another minimum spanning tree, T prime. So if E is also part of T, then nothing to prove, right? That satisfies the result. So let's suppose E is not part of T. We will show it is part of another MST, T prime. Okay, so what I'm going to do, I have a tree T, right, which is the MST that X was part of. And let's just add E to it, the new edge. So add E to T. T was already a tree, and I just added one more edge. I created a cycle. Do you agree? Or does anyone not agree? If I had a tree and I add one more edge, I necessarily create a cycle. For anyone that's unsure, my argument for it is the tree was connected, so it contained a path between the endpoints of the edge E, and now I just added the edge E. So that path that was in T plus the edge E has to make a cycle. Right? There was already a way to get between its endpoints, and now I added a second way. So follow that whole thing around, that creates a cycle. Okay, so this must create a cycle. Now, since we have a cycle, that means between the cut S and V minus S, we know that E crosses between, but since there's a cycle, there has to be another edge crossing in our tree crossing between S and V minus S. So let me write it, and then I'll draw a picture to hopefully help illustrate that. So the cycle must contain another edge across, or let me call the edge E prime. Across the cut S and V minus S. So it's going to look something like this. I have my graph. Let's draw it like this now. Let's say that our partial solution X, what color? Pink. Was this. And like we said, this part over here, was S, this was V minus S. And let's say that the actual tree that it's part of had this edge here. This is the edge E prime in T. And the shortest edge, the one I'm adding, is instead, sorry, I should draw. Is this one here. So this is the E. Right, so the tree is the 3 pink edges plus the green edge. That's the tree T. I added E to that tree, and it created this cycle, which is the square, you know, with 4, or like whatever that is, a parallelepiped, I don't know. Is that with the 4 edges. And now I'm saying, right, that's a cycle. And so I have now 2 edges crossing between S and V minus S. And my argument is just going to be easy. Like I'll tell you at a high level and then like implement it in words. But I'm going to say that if I just delete the edge delete the edge E prime from T and add the edge E to T, that has to be a new minimum spanning tree. And that's part of this new, like X union E is part of that thing, because X was the pink edges. The new edge I'm adding is the yellow one. And so I'm saying that that's part of a new minimum spanning tree, T prime. Yeah.
But T is already a minimum spanning tree. Yeah, if we're gonna add E, and E is
Yeah, that's exactly right. So actually what I'm going to argue is that E is like kind of the same length as E prime. You know, you're exactly right. You know, if I found a better edge crossing the cut, then I should actually just substitute in E for E prime in my solution, and I'd get a better spanning tree. But you're exactly right. That, like, if you follow that, then you basically are following this argument that it's got to be, adding E has to still be part of a minimum spanning tree. Okay, so there's my picture. So let's define T prime, which is T, add E to it, and subtract off E prime. Since T was connected and E prime created a cycle, I'm now deleting a cycle edge, right? That's from our property before. This graph right here has a cycle in it. Right? It's all the edges I've shown in the 3 colors. Deleting an edge, a cycle edge, cannot disconnect the graph, right? So the corresponding thing is still connected, T prime, and it must also be a tree. So T prime is also connected by property above, the first property. And T prime must be a tree. Maybe some people that's obvious that it's got to be a tree. For other people, maybe not. And the property I'm relying on there is that if I give you a graph on n vertices, it's connected and it has n-1 edges, it must be a tree. There's not enough edges for it to make a cycle, basically. And so since I know like T was a tree, right? So T had n-1 edges. I added an edge and took one away. I still have n-1 edges. And I know it's connected from that property above because I just deleted a cycle edge. So the result must be a tree. Sometimes that kind of question, like to argue that type of thing, that if you have a graph on V vertices and it has V minus 1 edges and it's connected, then it must be a tree. Like that's the type of thing that you could get asked on a midterm or final exam, you know, like, because it's actually quite easy to show if you don't agree with it. But yeah, anyway, that's all I'll say. So T must be a tree. And the length of T prime, T prime is equal to the length of T plus the length of the edge E minus the length I took away, the length of E prime. But length of E has to be less than or equal to the length of E prime, since E was the shortest edge crossing the cut. Therefore, the length of T prime is less than or equal to the length of T. If T was a minimum spanning tree, then certainly then T prime has to be a minimum spanning tree because it's at least as short. So that tells us then that X union E is part of an MST T prime. Okay. So why don't we take a 5-minute break and then we'll continue with how to implement this. Okay. So we now know that Kruskal's algorithm is correct. It computes a minimum spanning tree. The next question, which we kind of already talked a little bit about, is how to implement it. Well, I guess I skipped a point. We understand why the cut property holds, right? And now I just have to convince you why the cut property tells you Kruskal's algorithm is correct. I guess I didn't do that part yet. So what is this cut that we're adding an edge across in Kruskal's algorithm? So at each iteration, E prime in that Kruskal's algorithm I wrote above was the partial solution X, just a different notation. And the partial solution is a forest, right? We know it doesn't create any cycles. When we're building the tree, it's not yet a tree, so it has at least like 2 connected components. And so it's going to look something like this, right? Like we'll have, if I go back to my like standard example, why don't I add another edge? Something like this. And let's say our partial solution was, I guess I should draw it with the short edges, right? This edge and this edge, let's say. And so that partial solution is a forest, right? There's several trees in here. The trees are actually, there's this one, there's this one, there's this one, and there's this one. I mean, some of the trees are empty. They're just isolated vertices. And now when I add an edge, I'm adding the shortest edge that crosses between the connected component at one of its endpoints and all of the other vertices. So I don't know, I've drawn a bad picture. What's the shortest edge that, if these are the edge lengths, maybe that one's the shortest? I don't know. No, I'm saying that the length is like how long it looks on the page. Just so that I don't have to write numbers every time, to make it up. So like it's visual, yeah.
But that's not the strongest method.
Oh, sorry, yeah, I haven't drawn all my edges. You're right. Let me draw some more. I got to the part I wanted and then I stopped. I don't know. Let's make some more edges. Thanks, yeah. So these are my trees, I guess, like T1, T2, T3, T4. And then when I add an edge, its ends are in different connected components. So call them T1 and T2. Maybe that means the next edge that I add is going to be this one right here. I'm going to add the pink edge, E. Right? And so then E is the shortest edge that doesn't create a cycle, or in other words, it's the shortest edge crossing between T1 and V minus T1, or equivalently T2 and V minus T2. So it's like I created, my picture's getting too complicated, but I've got, like, let's say we take T1, then this is T1 here, and V minus T1 is all the other vertices, right? It's all of this. And the pink edge is the shortest edge crossing between that cut. And so at each iteration, I am adding the shortest edge that crosses a cut for an appropriately defined cut, right? S and V minus S. And so that E satisfies the cut property with that kind of definition of cut. And it must be that every edge added satisfies the cut property. And so E prime is part of an MST at each iteration of Kruskal's algorithm. Yeah.
So in the proof, like we have a cycle that, like let's say we have another edge, then we have a cycle. But then in this case, we didn't really add other edges within.
No. So the difference, I guess, is like this is now the construction that's occurring in Kruskal's algorithm, whereas the other was like, a proof of the cut property. Yeah, exactly. Now we're just applying cut property. I'm just trying to convince you that there isn't a cut for which E is the shortest edge crossing the cut. And that cut's just take one of its endpoints, take the connected component that endpoint is in, and then take all the other edges as, the rest of it. And that edge that we add crosses that cut. Okay. So now the question is, how do I check if a graph, if when I add an edge, it's going to create a cycle? So we need a good way to do this. And the idea is to use something called what they call a disjoint sets data structure. And it's fairly simple to describe and kind of clever. What it does is it stores each connected component of the current solution. So, and then when I go to add an edge, I look up what connected component is U in and what connected component is V in. If they're in the same connected component, I can't add it because it would create a cycle. If they're not, then I can add it. And if I add it, I then merge those two connected components together because now they've become one. Right? So at this point in my solution, before I've added the pink one, my disjoint sets data structure contains 4 connected components, right? Which I've written as like T1, the vertices in T1, T2, T3, and T4. And then when I'm trying to add the pink edge, I'm looking up what connected component is the top endpoint in. It would return to me, oh, it's in T1. And the bottom one, oh, it's in T2. Okay, I get to add it then. And then if I had, this edge here as a candidate. Both its endpoints are in T2, so I wouldn't get to add it. So the operations that we're going to have are make set. So it takes in an element and it makes a set, like a connected component that just contains that element X. So you can think of X as a vertex here. Disjoint sets data structures are used for other things than MST, but this is, in the MST case, X is a vertex. You can then run find on X, which says what connected component is X in. That's what we're going to do to check the endpoints. And then I need a way to merge, right? And so that's done with union between X and Y. X and Y are going to be the edge, the endpoints of the edge, and it will union the connected components containing X and the connected component containing Y. Any questions on the three operations before we go through them? Okay. So if we had these operations, then this is how we implement Kruskal's algorithm. It's pretty clean to write. So we have no edges in our partial solution to begin. So we create a connected component for every vertex. That's what's done in line 2 with make set of U for all vertices. We then start off our partial solution with nothing in it. It's the empty set. We sort the edges in line 4 by length in increasing order so that we're going to consider them from shortest to longest. And then we loop over all the edges in that order, right, from shortest to longest. When we're considering an edge UV, we find its one endpoint, what connected component is it in, and its other endpoint. If they're in different connected components, then we just add it to our partial solution and we union the connected components because now we've merged them together. Otherwise, we skip that edge, we go to the next shortest edge and try again. And that's it. So it's a fairly simple implementation, but of course we've now got these data structure operations, make set, find, and union. And so everything's going to hinge, the runtime is going to hinge on how many or how much that costs us to do each one of those. And so of course, like the runtime will depend on how we implement the data structure, but let's just count the number of each operation that we make, and then we can do like what we did with Dijkstra's algorithm once we've pinned down what the data structure looks like. So make set operations, we do V, right? One for each vertex. So V make set operations. Then we do how many find operations? Two E, that's right. 2E find operations. And then how many unions? Yeah. So could we really create a tree with 2E edges? Yeah, it's actually going to be V minus 1, right? The total number of edges we can add. You're right. I mean, E is an upper bound for sure. It's just that once we've added V minus 1 edges, we've created a tree, and so we've already got a solution. So V minus 1 unions. Another way to think of it is each union reduces the number of connected components by 1. And then we have to do a sort, right? We have to sort the edges by length. So that's going to take us E log E time, right? Because there's E edges. And then this argument, I think you've seen it maybe if you reviewed the midterm from 2020. What's the most number of edges a graph on V vertices can contain? Yeah, order V squared. You're like, and so log of V squared is 2 log of V, right? And so this is actually like big O of E log V. You see what I'm saying? It's E, well, it's less than or equal to E log V squared. There's at most V squared edges, which equals 2E log V. That's only going to come into play when I write the runtime. I'm going to write it with a log V in it instead of a log E. Yeah.
Why are we only subbing it in?
Yeah.
Sorry, for the E log, right? Why are we only subbing in for one?
Well, because here, like, it's capturing something different, right? Like E might not be as big as, we know that E is somewhere between V and V squared. But here it's actually telling us something. Like if E was only, if there's only V edges, this would be a better runtime, right? To say it's 2V log V rather than saying it's 2V squared log V. So I'm trying to get the tightest upper bound possible, but you can see it, when I sub in a V here for E, or a V squared for E, it only brings a 2 down in front. So it's like, when it gets all absorbed in the big O notation, it's just a constant. Okay, yeah. Sorting, line 4. Yeah, I should have written it though, right? That's probably what you're more commenting on. So sorting edges is E log E, which is E log V. Okay, so how do we do this data structure? Right now, I'm just going to add up all those times once I figure out the time per operation for my data structure. So the terminology, I just want to clear something up at the very beginning. We use a tree structure for each disjoint set, but the tree structure in the data structure has nothing to do with the minimum spanning tree. Do you know what I'm saying? We're computing a tree, but the one that I'm using to keep track of my disjoint sets, totally different. So don't think about what I'm going to draw now as being like partial solutions. They're just a way to bookkeep what's in a connected component. So in that tree, which is going to contain all the vertices in a connected component, the root of the tree serves as its label. So one of the vertices in that connected component will be at the root. Then we use these parent pointers, pi, that lead from any vertex. I can follow the parent pointers back up to tell me what the root of the tree is. And that root will then be what I like is the label of that connected component. Tells me which connected component I'm in. And then again, to sort of be able to do the union efficiently, I also keep track of the rank of a vertex, which is how deep does the tree go below me? So wherever I am in the tree, I just say like, how far down does it go below me? And I'm just going to use that to make sure that when I merge two trees together, I keep it as shallow as possible so that this following parent pointers up to the root doesn't take too long. So that's just sort of a thing that you'll see in a moment, I guess. So it might look like this. Let's say so we would say, for example, the parent of B equals A, or C, I mean. C, this is the root. And the rank of A here is going to be equal to 0. The rank of C is the height of the tree below it. And so it's going to be 2. Right, and all the ones have a parent pointer. I'm just giving one example of what it looks like. And C's parent is going to be itself. So make set then is easy. It's just I give a single vertex, right? And I want to make a set for the connected component. So I just basically, I take X and pi of X points to itself so that I know it's the parent, right? It's just and the rank is 0. There's no tree below it. Maybe that's confusing to draw. I don't know. I was trying to show that it points to itself, but then that doesn't look like a tree. So I'll delete that. That's not an actual edge, right? It's just a parent pointer. Okay. Find. All I do in find is just follow the pointers back up to the root. And so I'm going to do this recursively. Or I guess this one actually isn't recursive. Sorry, I'll do it recursively later. So in this implementation, I just say, well, pi x, well, its parent is not itself. Just go up a level, right? Set x to its parent and try again. And finally, when I hit the point where x is equal to itself, x's parent is equal to itself, then I'm at the root. And then I just return x. And then we have the merge operation. And like I said, to merge, all I'm going to do is point one tree to the root of the other. And I just do it in the way that makes it as shallow as possible, right? There's two options. I point the root of tree 1 to tree 2 or vice versa. And so I use rank to figure out which way to go. And so this union procedure looks long, but it's very simple. All I'm doing is I'm just checking which way to point it. So, and it's written a little bit wrong, I'm just noticing. It should take in 2 things, right? It should take in X and Y and union them together. I'll fix that after. So what do I do? Let me just read out what it says. So finally, to merge 2 sets, point the root of one tree to the root of the other. To keep trees shallow, we point the root with smaller rank to the root with larger rank. So we find what component is X in, what component is Y in. If they're in the same connected component, then I don't even have to merge. So I just exit out of my merge operation or union operation. So this is like already merged. Otherwise, I just check which one has a bigger rank. If the rank of X of the one that X is in is bigger than Y, then I point Y to the root of X. So I point the root of Y to the root of X. Otherwise, I point the root of X to the root of Y. And if they had the same height, if they had the same rank, then I've now increased the rank by 1. And so I just increment the rank of Y by 1 in that case. So let me just draw a quick picture that will, I think, make that even clearer. So if 2 trees have the same height, then we need to increase the rank of the new root by 1. And we don't have to change the rank of any of the other vertices. None of the other ones change. They're all correct still. So let's say I have this. This is one connected component, and this is the other. Right, so A is the root of one and D is the root of the other. They both have rank. Rank A is equal to 1. Rank D is equal to 1. And so after I do my union operation, it's going to look like A, just the original, the first one, ABC. And then I pointed the root of D. I've pointed D to the root of the other tree. So then it goes D and E, and then I have to increment the rank of A, right? Rank A equals 2 now. And all the other ranks are good. Yeah. It shouldn't be. Why? Do you see an issue or? No, we're going to run it on a node. It takes 2 nodes in the connected components, which will be actually the endpoints of the edge. So the inputs here are just 2 vertices. And then operation unions the connected components corresponding to those vertices. Yeah, think about it as the label of the connected component that it belongs to. It's the root, but the only reason I say not to say tree is because it's not the tree from the MST. Yeah, it's the tree in the data structure. But it's a good question, yeah. Okay, so the main thing, right? The only bottleneck in this, if you look at our operations, just quickly, make set is order 1, right? Find, let's skip for a second. Union, also order 1 operation. Well, sorry, no. Make set's bottleneck is going to be find, right? It does 2 finds, and then all of this is just, order 1 operations, and there's a finite number of them. There's 7 or whatever. So this is going to be dictated by 2 finds. And so the find, of course, depends on how long this while loop runs, which depends on the depth of the tree. And the depth of the tree you can show, which we won't go through the proof of it here, is order log V. So the maximum rank of any vertex is order log V. If you want the proof, if you go to the textbook, there's a proof of this. For us, I think it's okay to not do it. So, that's enough then to give us the runtime, which is, we then have make set is big O of 1. We have find is big O of log V. And we have union. It takes 2 finds, so it's big O of log V as well. And from that, then we can get Kruskal's runtime is going to be big O of, we have to do V make set operations plus, we have to do a find operation for each time we're trying to add an edge, right? We have to do find on each of its endpoints. So we have to do E finds, and each one costs us log V. So this first one is make set. These are our find. Then we have to do unions. As we said, we only had to do v minus 1 unions, right? So it's v log v. And then we have to do the sorting. And so if you look at what dominates, it's E multiplying log V. So the overall runtime is big O E log V. Okay, there's one little trick that we can do, which helps us out, and it's called path compression. The idea is just when I do a find on a vertex, I follow its pointers up to the root. I might as well just make its parent pointer the root at that point, rather than just leave, like, you know, in the current pseudocode, when I do the find, I don't actually adjust the parent pointers. I just follow it all the way up and find that the parent of this node X is whatever I return here. Or the root of it, sorry, is that. But I might as well rewire it, right? As I follow it up, just point each one of them back all the way to the root. So that's actually a very easy little fix that'll only help our runtime. It's called path compression. So it just looks like this. During each find, when parent pointers, it should say, parent pointers are followed to the root, change each pointer so it goes directly to the root. And here's a kind of clever piece of pseudocode that does that. Maybe you can try and just look at it for a second and convince yourself that it actually does that. So what am I doing here? I want to find the root for X. So same thing, while the parent is not the root, I then set the parent to be the root of its parent. That's then going to rewire pi of X to point all the way up to the root of the tree. And since it's doing it recursively, right, next, for that, it's a recursive call. So now I'm going to call find on the parent of X. It will actually reroute its pointer right up to the root, and so on. And then finally, that's, you know, this will then be rewired to the root, and so I return it at the end. Some people, I think when you look at that, you think that, why don't I set pi X to find of X? Like, why am I setting it to find of pi of X? Do you see a flaw in setting? Yeah? Yeah, exactly. Find X would then call itself exactly find of X, and it would just never terminate, right? So this is always ensuring to do find on X, I do find on the parent of X. To do find on the parent, I do find on its parent, and so on. So it actually goes up the tree. This, it's kind of a practical thing, like it's a no-brainer to do if you're implementing this, because it's like the same length of pseudocode, and yet it actually helps. In terms of asymptotic runtime, it doesn't really help that much, like in terms of our analysis, but it's like a practical improvement. So if you look at the amortized cost, which is the total runtime I spend across all find operations, and then divide it by the number of times I call find. For the original find, of course, that would be log V, right? Because that's what we did work per find. In this one, it's slightly more than 0.1, but less than log V. And I think I've seen elsewhere, it's not really in the text, like exactly, you know, a slightly tighter expression for this. But basically, it's a practical improvement that just helps a little bit in the runtime. Yeah. No ranks. That's a good question. I think you should update the ranks, right? Sorry, yeah, because basically after you rewire it, it's all, I guess all the ranks become 0 after you do path compression. And then the rank of the root becomes 1. Right? Because as you go up, you just point everything right to the root. But you're right, actually, there should be an update of the corresponding ranks. Yeah. That's a good question. I probably should include that in this as well. I wasn't thinking of that in this. Okay, that's all I wanted to cover. So that's Kruskal's algorithm. We're then going to give one more algorithm next week, or after reading week, I guess, which is called Prim's algorithm for doing the same thing, but it does it in a very different way. So, all right, have a great reading week, everyone.